I'd like to thank Luca and Loredana for the kind invitation and the opportunity to speak here. The material that I want to present today is joint work with Isabella Laba. It concerns the LP mapping properties of maximal averages on certain sparse subsets of R and associated density theorems. Let me begin by describing the problem and providing a bit of background. So given a decreasing sequence of sets Sk, contained in the interval 1 to 2, let's define the maximal operator M as follows. So M acting on F evaluated at X is simply the supremum of all the absolute values of the averages of F over sets of the form X plus R Sk, where the supremum is taken over all positive integers k and all positive dilations R. What's the problem? The goal is to study LP-LQ mapping properties. Of M. Now, the study of maximal operators has long been an extremely productive avenue of research in harmonic analysis. However, the introduction of yet another maximal function perhaps needs some justification. So let's begin by recalling some well-known results on maximal averages over hypersurfaces in Rn. A typical example is the spherical maximal function, which sends a function f of x to its maximal average over all spheres centered at x. And here sigma denotes the surface measure of the sphere in Rn. Now, it's a classical result of Stein from 1976 that if the dimension n is bigger than or equal to 3, then the maximal spherical operator is bounded on LP of Rn if and only if P is strictly larger than n over n minus 1. In 1986, Bourgain succeeded in extending this result to the case n equal to 2. And there was a follow-up proof due to Schlag as well as LP-LQ generalizations. since then, there has been many generalizations and extensions of results of this sort. Possibly the most relevant for us is a theorem of Rubio di Francia, which goes as follows. So suppose that mu is a compactly supported finite Borel measure in Rn, any n, with the additional property that the Fourier transform of mu decays like mod z to the minus a at infinity for some a strictly bigger than a half. Then the conclusion is that the maximal average T star where T sub t, as you can guess, is the multiplier is bounded on LP for P larger than 2a plus 1 over 2a. Okay. Why is this an extension? That's because this Rubio di Francia's theorem implies Stein's spherical maximal function result. However, it fails to recover Bourgain's circular maximal theorem because there the Fourier transform of the arc length measure on the circle falls exactly on the boundary. A is actually equal to 1/2 there. Okay. What makes this interesting for us and ties in with the question that I posed at the beginning of my talk is the following. So now suppose that mu is a singular measure on R, by which I mean that the support of mu is some set S whose Lebesgue measure is 0. Assume for good measure that it is compactly supported. Then it is known that mu hat of xi cannot decay any better than mod xi to the minus a half at best. And what's worse is, in fact, we do not know if there is a measure which satisfies this best case decay. In all known examples, there is typically either a logarithmic loss or an epsilon power loss compared to this decay mod xi to the minus a half at infinity. Okay. So at this point, this problem starts to bear at least some formal similarity with the Bourgain's maximal function estimates. Why? Because here is a measure mu, and one can create the operator T star associated to the measure mu exactly as Rubio di Francia did. However, this measure has epsilon worse Fourier decay than is required by Rubio di Francia's theorem. So, and furthermore, if you think of a typical Cantor type construction where this set S, the support of the measure mu, is the intersection of a nested sequence of approximations Sk, and mu is the weak star limit of the normalized Lebesgue measures on Sk, then the maximal operator T star considered by Rubio differentia is actually dominated by our maximal function M. So, any LP LQ mapping property of M that we can deduce would automatically translate to a generalization of Rubio differentia's theorem to the A smaller than 1/2 regime. And there is a second reason for considering such a question, and that's the issue of almost everywhere convergence results, which also goes by the name of density theorems or differentiation of integrals. While having a considerable overlap with the theory of maximal operators, density theorems have their own rich history and individual entity with important contributions by Busemann-Feller, Hayes and Pock, Jessen, Marcin, Kuit, Zygmunt, among many, many others. Undoubtedly, the most famous density theorem is the Lebesgue density theorem, which says that whenever you have a function f that is locally integrable, the averages of f over balls of radius r centered at x converge to f of x for almost every x as the balls shrink to the center x. In view of the key role that the Lebesgue density theorem plays in real analysis, it is natural to ask, and indeed it has been asked, whether it is canonical in some sense. In other words, is it the only density theorem that is somehow connected to the inherent algebraic structure of the reals, namely translation and dilation? And more specifically, the question is the following: do there exist either translation invariant or affine invariant families of sets which have the density property, just like the Lebesgue density theorem, but the density property is not a consequence of the Lebesgue density theorem. And the answer to this question has been partially addressed and answered. For the translation invariant case, the answer is yes. And it's independently due to Aversa. One answer result is due to Aversa and Price via a result known as the Hart's density theorem. And the second one is due to Stein using maximal operators. I am not going to state the Hart's density theorem, but here is an easy consequence. Suppose you look at the translation invariant family of sets generated by the intervals ik. Then the claim is that this translation invariant family of sets has the density property. In fact, so what does that mean? It means that if you look at these averages, they converge to f of x as k goes to infinity for almost every x, f locally integrable. However, you cannot retrieve this fact from the Lebesgue density theorem. Okay. However, so this is the answer to in the translation invariant case. For the affine invariant case, the question was left open, and it was formulated in the L2 setting as follows by Aversa and Price. Okay. So they ask the following question. Does there exist a sequence of sets Sk contained in the interval 1 to 2, a nested sequence, each sets Sk have positive Lebesgue measure which goes down to 0, such that for every function f in L2, if you look at these averages, not only do these averages go to f of x as r goes to 0, in fact they do so independently, uniformly in K. Okay. So once again, why is this relevant to the problem that I mentioned before? Because if you recall how I defined my maximal operator, it was precisely the average, the maximum of these averages. So if I can prove an L2 to LQ bound for such a maximal operator for any finite q between 1 and infinity, by standard techniques that would automatically translate to an affirmative answer to the question of Aversa and Price. Basically, exactly the same way Lebesgue density theorem follows from the weak type L1 bound of the Hardy-Littlewood maximal operator. Okay. So I think at this point I'm ready to state our main result, which does succeeds in doing the program that in the program that I set out. It provides an extension of Rubio-di-Francia's theorem to the A smaller than half regime, and it does answer the question of Aversa and Price. So given any epsilon positive, there exists a sequence of sets Sk as specified above, such that the following two properties hold. The maximal operator sends LP to LP for p larger than 2 plus epsilon. And number 2, there exists a finite q such that the maximal operator maps L2 to LQ, thereby answering yes to the question of Aversa and Price. So in the remainder of the talk, I am going to briefly sketch the main steps of the proof and describe the construction of the sets Sk. So the sets Sk are constructed using a random mechanism, and it's very easy to describe. So one starts with the interval S0, well, it's the full interval from 1 to 2, and one breaks it up into n equal pieces so that each subinterval is of length 1 over n. And now for each endpoint, we either select it or reject it according to a certain probability. So the mathematical way of describing it is you have an IID sequence of Bernoulli random variables with success probability p, and you pick out the endpoints for which the corresponding Bernoulli random variable has value 1. So let's say at the end of the day, these are the ones that got picked. Okay. Then we sort of append to each of these chosen points the corresponding subinterval of length 1 over n. And the union of these subintervals gives me my first approximation, S1. And at the next step, I play the same game. I take one of the chosen intervals from each of the chosen intervals from S1, break that into n equal pieces. So now each subinterval is of length 1 over n squared. And again, pick certain endpoints using a probabilistic procedure and keep going. Okay? So at each stage, my approximation Sk is a finite disjoint union of subintervals of length n to the minus k. And if you see, there is a large number, there's a huge sample space of possible ways of choosing the selected subintervals. All right? The real challenge is to prove that there exists some realization in this sample space which satisfies a list of criteria that are going to help us get to the subsequent maximal function estimates, because that's our goal. We need to prove that a maximal function satisfies certain LP bounds, and the challenge is to pick a realization and to show that there exists a realization for which certain estimates will hold true. So in order to understand what this list of criteria are and how they govern this random selection, let's try to understand how to control the maximal function. Now, there are certain preliminary reductions to be made before I can actually get to the heart of the affair, but all of these reductions are very standard, so I'm just going to mention them without getting into the proof. First of all, even though the dilation is over all positive R, it suffices to restrict only to the scale where R is approximately of the size 1 between half and 2, say. Second of all, we decompose our measure mu, the limiting measure, as a sum, as a telescoping sum. So what are the phi k's? Each phi k is the normalized Lebesgue measure on the approximating set Sk. So the sigma k's, each sigma k is a signed measure with a whole lot of cancellation built into it. It integrates to 0. The phi k's are all probability measures, by the way. And once you finish this decomposition, that translates to the following sum. M is dominated by the sum of the mk's. Where mk, as you can well guess, it's the maximal operator associated to the signed measure, sigma k. Okay. There is one last reduction step, again fairly standard, which is linearization and dualization. So what does that mean? That means that instead of looking at the operator mk and proving an LP estimate on it, I am going to first linearize the operator by replacing this sup over R by a measurable function R which depends on x. So, and then looking at its formal adjoint. So I'll be looking at this linearized dualized operator And what is Vx? Vx is simply an affine copy of the measure sigma k. And R sub x is the linearizing function. It's a scale factor which is a measurable function of x. So the point is, it suffices to prove, so the goal, the revised goal I should say, is to prove the following LP to LP estimate for the adjoint operator. In the dual range. And now paying close attention to the fact that at the end of the day, I have to sum up all these mk's, so my operator norm alpha k had better be summable in k. All right, so those are all my reductions. And one final comment, even though I have stated a strong type bound, it suffices to only get restricted weak type PP bounds. So restricted weak type. Since then, a standard interpolation theorem will take care of the rest. All right. So, in order to understand how to get to a restricted weak type PP bound like the one that I have just now written down, let's try to revisit an argument of Bourgain. I already said why this problem has certain features of similarity with Bourgain's circular maximal function estimates, and you are going to see that this will be a recurring theme in this talk. So here's an argument. On the circular maximal function. So he too was looking at the two-dimensional analog of the spherical maximal function, and he did exactly the same reductions that I have just now talked about. He wrote sigma as the telescoping sum sigma k, and he was reduced to proving an LP to LP bound on the linearized dualized operator with summable operator norms. And he did this by making the following observation. He first said that there are two trivial estimates. What are they? So there are two one is an L1 to L1 bound, and this is truly trivial. This is just Fubini's theorem in disguise. And there is also an L2 to L2 bound, which has a Fourier analytic proof. And there the operator norm grows linearly in K. Notice that by themselves, neither of these estimates would work for us. After all, the operator norms are not summable, and in fact the L2 to L2 bound is slightly worse in this respect because it blows up. Okay? What Bourgain said was, all right, we are after a restricted PP bound for P between 1 and 2 after all. So if you are given an input function f, which is the characteristic function of a measurable set omega, let's decompose omega into two parts, omega naught and omega 1. So that if you now look at the maximal operator on the indicator function of omega naught, that will have a geometric decay. Okay? And similarly, you can guess what's coming next. If you look at omega 1, its L2 norm will be better than expected. So here G is omega naught, which is the L1 norm of omega, and this is the L2 norm of the indicator function of omega 1. So this was his idea, and if we can do this, then we are done. Why? Okay, let's call this 1, let's call this 2, let's call this 1 prime, and let's call this 2 prime. Because now it's just a question of interpolation between 1 and 1 prime, 2 and 2 prime. The geometric decay is enough to get some ability, so we are done. All right, so a lot of this is actually going to work out for us as well. So let's go back and see how much of this we can make work. So if we look at, we still have 1. 1 still works out for us. 2 is in fact replaced by something slightly worse, and again that is to be expected because typically our Fourier decay is slightly worse than the Fourier decay for the measure on the circle. So what we actually have is a small geometric blow up like that. But supposing we can do the same kind of decomposition that Bourgain did and happen to get a better than expected L1 to L1 improvement and an L2 to L2 improvement, then once again interpolation ought to help us out. Okay. So the question is, how on earth does one go about improving, say, the L2 to L2 estimate? So how to improve the L2 to L2 bound. And there is a very easy way of seeing it. All you have to do is look at the maximal operator. So we are going to look at the maximal operator K star acting on one of these characteristic functions, and let's look at its L2 norm squared. And if you just write it out, what its formula is, and take 2 copies and integrate, what it gives you, remember, mk star is integration against these affine copies of sigma k, which we call Vx, etc. So it's just an identity which shows that the L2 norm is that. But that already tells us what we should be looking at. We should be looking at this thing right here. What does it measure? So this measures the size of the intersection between 2 affine copies of the signed measured sigma k, and because it is signed, I have to pay attention to cancellation. So if I want to improve an L2 to L2 bound, I really should get my grip on how 2 affine copies of sigma k intersect. All right. Unfortunately, all similarities to the circular maximal theorem end here. Why? Because after all, they were working with circles, and we are very far away from circles. For Bourgain and Schlag, considerable effort was spent in trying to understand intersection properties of circles or families of thin annuli on the plane. So if you okay, so here's the picture, and this is courtesy of Isabella. So if you remember how Bourgain and Schlag's argument went, they tried to understand what's the enemy when you have families of circles intersecting. And one of their arguments was that as long as you have transverse intersection, and a transverse intersection is sort of dictated by this blue circle and this little pink circle here, So that's a transverse intersection. The size of the intersection is small. Whereas if you have your enemy, or when you have families of circles with large internal tangency, and then the size of the intersection is large. So a lot of their efforts went into into controlling the size of these internal tangencies. In our case, we do not have any of the geometry of the circles, but what is astonishing, it's strange to me, that we can come up with certain versions of the notions of internal tangency and transverse intersection. So let me try to sort of talk about that in the last few minutes. Okay, so suppose we have two copies, x plus rsk and y plus tsk, two copies of our sets sk, and let's say that they intersect. What does that mean? That means that there has to exist a pair of indices, or many pairs of indices actually, such that if you think of sk as the union of a certain number of disjoint intervals, then the ith interval of one must intersect the jth interval of the other. So these are all trivial comments. However, now two cases can arise. Either I and j could be close to each other, say less than a 10, or they could be far apart. And I want to call this kind of an intersection an internal tangency, and I want to call this a transverse intersection. So unlike circles, now even one single intersection of two affine copies of sigma k could have a certain number of internal tangencies and a certain number of transverse intersections. And the thing to notice is if you have two copies of sk with a large amount of internal tangency, that is very restrictive. It means a large size between the inner product, that's true, but it forces x and y to be close to each other. So large internal tangency implies that x minus y is small, and that leads to an improved L1 estimate. So the real challenge here is to control the transverse intersection. So this is really the crux of the matter. And this is where the actual probabilistic structure of the sets sk is needed. This is something that I have been shelving for so far, but this is where it comes into play. Now, how does one control the transverse intersection? And this is where our main tool are the so-called large deviation inequalities. So I won't be able to get into details, but what are large deviation inequalities? We have already seen two examples of large deviation inequalities in Michael's talk and also in Dimitri Bilik's talk. So they were talking about the central limit theorem and the Khinchin's inequality. So we are more interested in the Bernstein type inequalities, and these large deviation inequalities refer to a body of estimates which, roughly speaking, say that under certain assumptions, if you have a large number of random variables, the average of the random variables having a high discrepancy from its expected value, the probability of such an event is exponentially small. And that is crucial to us in controlling the transverse intersections. Because remember, the way we generated our sets, there were all these sums of Bernoulli random variables that were built into the construction. And if we wanted to look at the signed measures, which gave rise to a large number of random variables with mean 0, and we were looking at the superposition of such things, that's where the Bernstein type inequalities played an important role. So I won't go into any more details. Let me just conclude by saying that we are trying to refine our analysis at the moment by trying to get the optimal range of P for the maximal operator that we have just described. And we're also trying to understand other associated structure of the sets Sk and how it depends on different choices of parameters. Thank you very much. Right. So what we are what this is pointing towards at the moment is that, remember how for Stein's maximal function, we have the optimal range is n over n minus 1 to infinity. Okay. So what we are seeing is, as you take epsilon, which is, so if 1 minus epsilon is, say, the Hausdorff dimension of the set, then as epsilon goes to 0, we can bring it arbitrarily close to 1. Yes? So higher dimensions as in sparse sets in higher dimensions? Yes, absolutely, because of course, once again, eventually it boils down to an understanding of how the random variables interact. And I think there is nothing that's extremely crucial about the one-dimensional nature. The reason we are looking at it in one dimension, because there are these it's a natural way of generalizing these higher dimensional maximal averages over hypersurfaces. But of course, the next thing to look at would be sparse sets in high dimensions. That's right.